previously we had different magnitude responses like this, for example, or it was changing with respect to the order, it was changing its characteristic. But ideal filters have two bands, which one of them is called pass band, the other one is called stop band. In the pass band, we pass all the frequencies as they are without any filtering effects, and we will remove all the frequency components in our signal which is beyond this cutoff frequency. Okay, gain is 1 for wanted parts, pass band. Gain is 0 for unwanted parts, stop band. Is that clear arkadaşlar? Okay. So how do you find h of n of this filter arkadaşlar? How do you find the h of n of this filter? This is the frequency response, magnitude response actually. This is the magnitude response. Why is it magnitude? Because we have the magnitude here, right? This is the frequency response and this is the magnitude response. How do you come from here back to h of n?
Inverse Fourier transform.
Inverse Fourier transform, right? We use inverse Fourier transform. How was the inverse Fourier transform like? Do you remember this relationship? Like this was our like frequency response, and this was our impulse response, a kind of sync function. Do you remember this concept a while ago that we have covered together? Yes? So arkadaşlar, if you take the inverse Fourier transform of such a filter, which is a low pass filter, its impulse response will be like this. Okay, this one is the h of n, which is a sync function. Okay, sine omega c times n times pi n. So it is a kind of it's a kind of function which goes to infinity, plus infinity and minus infinity. Okay, so because there is no un here, okay, it is valid for all n's. You remember this formulation here? From minus omega c to omega c, it is true for all n's, and it is sine omega c divided by pi, omega cn divided by pi n. Okay? If you remember, the sync function was like sine x divided by x. Okay? General formulation is like this. Sine x times divided by x. So, what is the problem with this impulse response? It is very long. It is of FIR. There is no like something divided by something, right? If I want to write h of n of this, Dirac n times 0.2, you see 0.2 here, times let's say 0. Plus 0.19 Dirac n minus 1, and so on, and plus 0. Minus 0 plus 0.19 Dirac n plus 1, and to the negative side, right? So this is this one, this is this one, this is this one. So there is no feedback. That's why it is FIR. But interestingly, it is like going to infinity. Anlıyor muyuz burayı arkadaşlar? It is very long. So in terms of frequency domain, it is perfect because it is passing all wanted signals by multiplying by 1, and it is removing all unwanted parts by multiplying by 0. Life is trade-off. You gain something, you lose something. You gain something, you lose something. You gain excellent frequency domain characteristics, but you lose time domain characteristics. Why? Because now my h of n is very long. Very long means a huge time, processing time for my let's say filter. It is not causal. It is highly long. That means there is a huge processing time for this filter to be used. Anlıyor muyuz buraya arkadaşlar? Because you know X of n convolved with H of n is my filter output, right? I have to multiply all X of n's and H of n's like with some convolution properties and will obtain my Y of n. There is also a problem called ringing effect. Okay, ringing effect means there will be a kind of instability in your signal. Okay, there will be a blurring, bozulma, bulanıklaşma, a blurring in your signal or image. So that's why, even though it's an ideal filter, it has perfect frequency component, frequency characteristics, but in terms of time domain characteristics, it is not ideal. Okay, in terms of time domain, we usually want shorter impulse responses. But shorter impulse responses will cause worse frequency domain characteristics. Anlaşıldı mı burası acaba arkadaşlar? Okay, so if we gain something in time, we lose something in frequency. If we gain something in frequency, we lose something in time. Okay, this is a kind of very important property that you should be knowing in signals and systems concepts. Okay, this is true for sampling. This is true for, let's say, pulse widths that we have. If I have pulse widths like that, like short pulse widths will correspond to longer frequency bands, and longer pulse widths will correspond to shorter frequency bands. So it has their own positive and negative sides, okay? So this is critical. Did everybody understand what is ideal filters? Okay, it is good in a sense, but it is not good in another sense, okay? So that is why we try to lose something by adding some ripples. Ripple, iniş çıkış, ripple, okay? Ripple. Small deviations from the ideal case. Small deviations in the ideal case. For example, if you have a sine wave like this, and you have ripples like that, okay, this is ripple. Small deviations from the signal, okay, from the actual thing. Anlıyor muyuz ripple, okay? So, ideal filter was like this. Now I'm adding some ripples here so that I will obtain a better time domain property and not so good as ideal filters, but good, let's say, frequency domain properties. Okay? So, in ideal case, it was like this, like abrupt change, okay, instant change, but here we have a transition, geçiş bandı, transition band. Okay, this is the transition band. This is pass band, this is stop band, but there's a transition band. Okay, it is like a car, you're not stopping it right now, but you are pushing on the brakes slowly, and then you will come to a stop. You will come to a full stop, okay? So you have a pass band like that, you have a stop band like that. Butterworth, Chebychev, elliptic filters have these ripples or kind of transition like that. They have a good, let's say, time domain characteristics with simpler transfer functions, but in terms of frequency domain, there will be a kind of small ripples in our filter. What is the effect of this ripple arkadaşlar? I want you to write to the chat. What is the effect of this ripple for our filter in terms of our output? Okay, I have my input signal, X of n, and I will have my filter, H of n, and I will have my output, Y of n. What if I have a ripple in the pass band and stop band instead of a sharp thing like that, an ideal filter like that, in terms of frequency domain characteristics? Süleyman said noisy output. Arkadaşlar, what did I say? In ideal filters, the impulse response is infinite length, which will cause blurring effects and computation time problems. We will change and have a ripple, but we will have a better impulse response in time domain. But in frequency domain, what is the effect in frequency domain? That's my question here. Iqbal, what do you mean by we don't get a real sharpness with ripples? What do you mean by sharpness with ripples? Iqbal, do you hear me?
Yes, hocam. If we have these like ripples, we don't get we don't close to ideal case. That's what I mean. But you asked something different, I guess.
What is the effect of having such a ripple? My question is, what is the effect of such a ripple in frequency domain in terms of filter characteristic? The effect of such a filter.
I don't know, hocam.
Okay. Any other? Süleyman, what do you mean by noisy output?
I assume that if we have, in normal case, ideal case, we have a perfect filter process, then we have a very good and precise output. If we go forward and non-ideal filtering process, if we apply non-ideal filtering process, we get something noisy with unwanted signals.
Unwanted signals, okay. Thank you. Mustafa Turhan, what do you mean by attenuation will not be the same everywhere? What do you mean by that?
In the frequency response.
Arkadaşlar, this is the frequency response, right? Normally, for each frequency value, at different frequency values, the ideal filter was always applying, multiplying by 1, right? But now, what is the attenuation? It is something like this here. For another frequency, it is something like that. For another frequency like that. For another frequency like that. So different frequency components will not be multiplied with 1 all the time, but will be multiplied with different values. So the attenuation levels of each frequency will be somewhat different from each other. Burası anlaşıldı mı acaba arkadaşlar? The attenuation level in my filter, because this is my frequency response. What does this mean? What does this mean? There is a variation. There is a variation in my magnitude response, right? For each frequency level, I will have a different attenuation level, different multiplication number. is that part clear arkadaşlar? Did you understand what I'm talking about? Yes?
Yes, hocam. What
Yes.
about its time scale?
What's that?
What about its time scale?
In terms of time, the bad effects like ringing or blurring will be better, okay? We will get rid of, or we will have less ringing effects.
I mean, before, if we have ideal filter, we get the sync function.
Yes?
What about its time function?
If you remember arkadaşlar, usually these kind of filters are not FIR filters. They are IIR filters, okay? Usually, as I said, FIR filters are represented with H of n, but IIR filters, we don't use H of n. Instead, we use H of z, or H e to the j omega. Why? Because I cannot write a proper H of n is equal to Dirac and this and that. It is infinitely long. Instead, I have H of z. It will have a numerator and a denominator, which will show us the relationship between input and the output. Okay? So it is somewhat, in terms of time domain, there will still be a kind of filtering, but what kind of a filtering will it have? There will be y of n is equal to y of n minus 1 or something like that. So we will have this kind of an effect in our filters like Butterworth, Chebychev, or elliptic filters, okay? So in terms of H of n, I cannot write immediately the H of n. I cannot plot in immediately H of n, just as I have done with FIR filters. But you have to think in terms of, here we have a feedback, and we have both y of n and x of n's in our discrete difference equation stuff, okay? Arkadaşlar, the critical point here is this transition band is also very important for us. It may be long or short. Sharpness of the filter. Do you remember this in circuit theory? How do we increase the sharpness of the filter?
Quality factor.
How do you increase the quality factor?
Decrease the bandwidth of our.
Using like, what are you doing in your circuit designs arkadaşlar? How do you change the circuit design such that a higher quality factor will be obtained?
Higher order filters, like second order, third order.
Yeah, we can increase the order.
If we increase the order arkadaşlar, this transition band will be narrower. Okay? If I increase the order of my filter, and then the transition band will be narrower. Okay? Emre, you want to ask a question?
Yes, hocam. In our circuit designs, we are usually using the normal circuits. I don't know, it's not digital filters, and there aren't such a ripples in our circuits outputs in the frequency things. But in this case, there's a ripples, and I mean those ripples cause some like a misunderstanding. Like each frequency treated differently. Like there aren't any rule.
Exactly. The effect here is very small. That's why we are gaining something here. Okay. For example, in your designs, you may have such a filter characteristic. Okay. You may have such a filter characteristic, for example. Then the transition band is really high. Okay. So in order to have a sharper filter like that, you have to use more op-amps, more resistors, more capacitors. What are we doing here with Butterworth, Chebychev, and Elliptic? We use less components, but we obtain a sharper transition. We obtain a sharper filter. with the expense of having some ripples. Burası anlaşıldı mı acaba? We are losing the exact 1-0 multiplication stuff in our frequency response, but at the expense of having some ripples, I will have a sharper filter. Why sharper filters are important arkadaşlar? Why do we need sharper filters? Nuri Can, why do we need sharper filters, my friend? Nuri is away. I think he is away. Ahmet Güney, what do you think? Why do we need sharper filters?
Hocam, sharper filters are avoiding noise better than low order filters. I mean, it is better to use sharper filters to get rid of noise better.
How do you get rid of noise better when you have a let's say narrower transition?
Narrower transition means a sharper filter, hocam, you said,
Yes.
as you said.
Yes.
So if we use more sharper filter, it means that we can filter better.
Filter better means like this, değil mi arkadaşlar? For example, I have a filter for an ideal filter. Let's say my cutoff frequency is 100 hertz. For 99 hertz, what is the attenuation level?
1.
1. For 101 hertz, what is the attenuation level?
0.
0. So I can differentiate and filter sharply between two very close frequencies, right? I have a signal which has 99 hertz and 101 hertz. I would like to get rid of this one and keep this one in place. How do I do it? I need a very sharp filter.
Hocam, we can say, emphasize the details of the signal.
You really keep the ones that you want in place, and you really have the opportunity to get rid of the unwanted parts.
Okay.
But for example, arkadaşlar, you have an alpha filter, alpha wave filter. What is the cutoff frequency? Let's say between 8 and 13 hertz, right? Değil mi? 7, 13, 7, 12, 8, 13, something like that. Okay. So you have a bandwidth filter, band pass filter. If it is not sharp, what will be the band pass filter like? Like this. And cutoff will be, let's say 8, cutoff will be 13. How about 14, 15, 16, 17? Or 7, 6, Süleyman?
Also includes the theta and beta signals.
So somewhat, if your filter is not sharp, arkadaşlar, some information from delta or beta or theta will be interfering with my band of interest, right? If I have such a filter, very sharp one, whose cutoff frequency is again 13 and 8. What is the attenuation level for, let's say, 6 hertz? 0, right? Almost 0. What is the attenuation level for 14? It is almost 0. So I don't allow other bands to interfere with my calculations, with my power calculations. If you are using only 2 order, second order, or third order filter, band pass, or 2 times that value in the band pass, or 2 second order in the low pass, then you will have a slower transition, which will cause other unwanted signals to interfere, karışmak, to interfere into your signal, and it will not be a good filtering realization. Anlıyor muyuz arkadaşlar? Transition band is such important thing. We have to be careful about transition band. what is the expense of increased sharpness? Higher order filters, more delay, more components, more computation time. Anlıyor muyuz burayı? If you are coming up with a continuous filter, analog filter, continuous time working filter, analog filter. If you have a sharper filter, you have to go, let's say, up to 6th level Butterworth, 6th order Butterworth filter, or 4th order Butterworth filter. That means you're going to need more op-amps. In digital world, if you go up to 10th order filter, then you have to wait for the first input to come even later. There will be a delay in your system. Anlıyor muyuz arkadaşlar? You are gaining something in terms of frequency domain, but you are losing something in terms of time domain. Bakın, here it says lower order realization, less computation. Lower order realization means there will be like z to the power -1 divided by, let's say, 1 plus and 1 plus alpha, or 1 minus alpha z to the power -1. Lower order, bakın, lower order, or 2, lower order realization. We will use, our orders of filters will be less. Okay? Şimdi buradan ben şu şeye geçmek istiyorum arkadaşlar. Let me resume, sorry. Arkadaşlar, what was the dB? 10 log V1 divided by V2. Okay, this is the dB level, right?
20 log.
20.
Isn't it 20?
For powers, what is it?
10.
For powers, it is 10. For this, it is 20. Is that the case, arkadaşlar?
Yes, in circuit we use 20.
Yes. So for this voltage, it is like this, right? 20 times log this. It's going to be dB in the ratio. So I found 100 dB. What does it mean? It is log 10 V1 over V2 is equal to 100 divided by 20, which is 5. V1 divided by V2 will be 10 to the power 5, which is 100,000. What does that mean, arkadaşlar? Input will be attenuated to its 1 over 100,000. So if I have 1 volt input, the filter has, if the filter has 100 dB attenuation, then the output will be what? 1 over 100,000. This will be the output.
Shouldn't we write V out over V in?
Then arkadaşlar, what I'm saying is, if it says 100 dB attenuation, what does it mean? V in, there is a kind of attenuation of 100 dB between V in and V out, right? This will be attenuated to become V out. Attenuated means I will multiply this by 1 over 100,000, right? Attenuation. Attenuation means I'm multiplying the input by a certain factor. Is that correct?
Yes, hocam. When we do the V out over V in, we get the like reversed version. So
yes.
That's true.
So it is the main logic. I'm trying to give you the main logic here. If it says 100 dB attenuation, 100 dB attenuation, it means my input will be multiplied by 1 over 100,000 and obtain the output in such a very low level. It will be almost microvolts. My input is 1 volt. The output is like 10 microvolts. It is highly attenuated. if I have a filter like this, okay, whose explanation was like that. Let me show you again. Yani bunları okuyabilmenizi arzu ediyorum aslında değerli arkadaşlar. So this is attenuation. If you see it here, it's like 100 dB, okay? So that means a factor of 10 increase in frequency beyond the cutoff frequency. So there is such a Butterworth filter characteristic, okay? If you go to Chebychev filter, arkadaşlar, here is the trick. In Chebychev filter, there is a ripple here. No ripple here. Yani aslında arkadaşlar, it is totally mathematics. We are trying to find out such numerator divided by denominator polynomials, and then for different x, we are trying to obtain such characteristics. It is totally mathematics, actually. Chebychev, Butterworth, these are all mathematicians. Okay, and they come up with such polynomials that will change its characteristic with some polynomials. Okay, Butterworth polynomial, Chebychev polynomial, or elliptic polynomial. They are going to be different. They have different polynomials, numerator divided by denominator. So in Butterworth, flat response in the pass band and stop band. In Chebychev, we have a ripple in the pass band and no ripple in the stop band. And if I increase the order, you see it's going to be sharper. When you see it here, it is slower. But here it is sharper, even with order 2. Bakın ne diyor? Chebychev filter can achieve a sharper transition between the pass band and stop band with a lower order filter. Yani if you design a Chebychev filter with order 2, you're going to obtain a better transition band characteristic when you compare it with order 5 Butterworth filter, for example. That means less number of components and less complicated, let's say, computations. Arkadaşlar anlıyor muyuz? Bakın, Chebychev filter produces smaller absolute errors and faster execution speeds than Butterworth filter. Yani it's a better filter than a Butterworth filter. Okay? Chebychev 1, pass band ripple. Chebychev 2, stop band ripple. Okay, stop band ripple. So we lose something in the stop band, but we gain something in the pass band here. Okay, same advantages over Butterworth filter. How about elliptic filter arkadaşlar? Ripples on both sides. Butterworth, no ripple. Chebychev, ripple, pass band or stop band, Chebychev 1, Chebychev 2. And elliptic filter, both ripples, but elliptic filters will provide the sharpest transition between the pass band and the stop bands. That's why it is widely used. Elliptic filters are more used than Chebychev or Butterworth filters. Okay, so there are nice comparisons on the web. You can find these, but I want you to understand this ripple concept. Ripple means better transition, better discrimination power, but it will be faster for elliptic and Chebychev than a Butterworth filter. And these are the things that I wanted to share for this part, arkadaşlar. Any questions until now? So filters, FIR filters, IR filters. Emre, you have a question?
If there is a more ripple in our filter design, can we say its delay of the R filter is lower?
The ripple, arkadaşlar, in design IIR design filter code that you used in MATLAB. Do you remember that? There are also filter design tools or things that you can check this on your own. If you increase the amount of ripple, you will have a sharper transition, okay? But sharper transition will cost more ripples. Higher orders will cause more ripples, okay? So you're losing something with including more ripples, but you are obtaining a better transition characteristic. Okay, that's the trick.
But for the execution speed, like the hour delay is lower for the sharper filters. Can we say those kind of comments?
If I increase the order, if I increase the Butterworth, second order, third order, fourth order, which one is the fastest?
First.
Second order.
Second.
The smallest order means fastest execution time. But Butterworth, Chebychev, or Elliptic, when you compare them with the same second order, their computation time will not be so affected, but the sharpness will be affected. Okay? Yani second order, all of them second order, similar computation cost. But what is the gain for second order elliptic? We will have a sharper filter when you compare it with a second order Butterworth. Anlıyoruz değil mi? Yani in terms of computation cost, second orders are comparable, but for second order elliptic, we have a sharper transition when you compare it with Butterworth second order filter. IIR, FIR, linear phase. Understand why this is IIR or FIR. Okay, what was the linear phase concept? Symmetric, anti-symmetric, and then we will have a constant delay in our... Arkadaşlar bir şey daha söyleyeyim, bir saniye. Son saniye bitiriyorum. Bugünkü quizde işinize yarayabilir. So, arkadaşlar, delay was D, right? D. In terms of samples. In terms of samples. So if we find D is equal to 1,
1 TS.
It says it is one sample. If I tell you, if my sampling frequency is 100 Hertz, what is the delay in terms of delay in seconds? How do you find it?
10 to minus 2.
Yeah.
One sample times 1 over 100 arkadaşlar. Okay? So this is my TS, sampling period. 1 over TS is equal to FS. 1 over FS is equal to TS. That means if I give you 100 Hertz, it means 1 over 100 seconds. One sample. If there is one sample delay, the input will be delayed by 1 over 100. That means 10 millisecond delay. If it is 1000 Hertz, it's going to be 1 millisecond delay. 1 times 1 over 1000. Anlıyoruz değil mi arkadaşlar burayı? So that's the trick. I want you to remember these couple of things. I hope you're going to get 100 from this quiz. It's not so difficult. Inshallah, you will do the best. Next week, Friday, we will have the final exam. We will be together, like you will have around 2 hours, and then we will have a kind of similar thing that we had in integrated quiz, but it will mainly focus on our subcomponents. Non-capsule students will attend the same one, arkadaşlar. Non-capsule students will attend the same final with capsule students because it will be a component-wise final exam. Anlıyor muyuz gençler? Başarılar diliyorum. I wish you all success and in finals and have a good relaxation time in the term break, and then we will meet inshallah in Math 301 statistics, probability and statistics course next semester with electrical engineers, and hope to see you in the final and then in the demo, and then after in the second week we will have the demo arkadaşlar. Second week of finals. Okay, after all your finals are over, we will have the demo of your projects. Okay. Görüşmek üzere. Hepinize iyi günler diliyorum.
Well, we're
Yes.
supposed to have a quiz today. You talked of 110 that we're supposed to have a quiz. I don't know.
Anya, what's that?
Are we supposed to have a quiz today?
From Signals and Systems?
Yes.
There is an integrated quiz tonight, this evening at 4 o'clock. There is no quiz for non-capsule students for now.
Okay.
Okay? Görüşmek üzere arkadaşlar. Hoşça kalın. Kolay gelsin.
See you hocam. Thank you.
Thank you.